Hi, my name is Prapavarin Channamsin.
And my name is Hau-Ping Ting.
And we will be discussing about green gasoline or biobutanol today.
As the fossil fuel deposit around the world is projected to be completely depleted in 53 years, a substitution for petroleum-based fuel, biobutanol, has received great attention in hoping to continue fueling human civilization in a sustainable fashion.
Biobutanol refers to biomass-derived butanol from fermentation of sugar in organic feedstocks such as corn. Its chemical formula is C4H9OH and is primarily used as a fuel in an internal combustion engine. The main focus of the project is the ABE or acetone butanol ethanol bacterial fermentation process.
From a historical data as presented by the U.S. Energy Information Administration, a six-fold increase in biofuel production took place from 2001 to 2011.
Since then, biobutanol has been intensely investigated and its market is forecast to reach $9.9 billion USD by 2020. The significance of biobutanol production is its environmental effect to reduce greenhouse gas emission by 20%. Having similar properties and energy content to gasoline, it can be used in its pure or blended form in any concentration with gasoline. Therefore, biobutanol may be the best hope in combating fossil fuel depletion, rising oil prices, and global warming. Environmental impacts, social impacts, and safety hazards are considered for the proposed design. Environmentally, wastewater disposal and treatment of hydrogen and carbon dioxide gas produced need to be considered. Corn production process and transportation need also be considered. Moving on to the social aspect, employee safety and public acceptability of substrate choice, particularly if the substrate is also a food source, should also be considered. Safety hazards. Butanol is harmful if swallowed, irritating to skin, and may cause drowsiness. Exposure may occur during cleaning, maintenance, transfer, sampling, and analysis. Because of this, workers should be wearing tightly fitting safety glasses, boots, neoprene gloves, and respirator if ventilation is insufficient. The ABE production process can be summarized with 3 steps: hydrolysis, fermentation, and recovery. Acid hydrolysis and enzymatic hydrolysis gelatinize cornstarch and cellulose in the corn kernel. The main goal of the hydrolysis step is to release fermentable glucose by breaking down the carbohydrate chain.
In the fermentation step, glucose is taken in by the Clostridium acetobutylicum bacteria cells and fermented anaerobically to ABE. The fermentation step yields 3 parts of acetone, 6 parts of biobutanol, and 1 part of ethanol. Moving on to the recovery stage, ABE separation is done through a system of distillation columns, taking advantage of the difference in volatility and boiling points. In the proposed design, this recovery approach is included in the plant downstream. The proposed integrated design is shown in the process flow diagram. The process inside the dashed box represents the conventional fermentation process. In the proposed continuous fermentation design, corn mash enters the fermenter with bacterial cells already present in it. Because a maximum concentration of 13 grams per liter of butanol cannot be exceeded for the bacteria to continue producing butanol, one stream is continuously withdrawn from the fermentation broth and passed through a heat exchanger to sustain the desired evaporation rate. In the vacuum flash unit, the stream is partially vaporized into an ABE-rich vapor phase and an ABE-depleted liquid phase. The ABE-depleted liquid bottom stream is withdrawn and passed through membrane filtration and recycled back into the fermenter, while the ABE-rich vapor top stream is cooled and separated by a 2-phase separator. The top stream leaving the separator is enriched in volatile organic compounds and compressed for adsorption. The bottom stream leaving the separator is the ABE solvent stream and also compressed for recovery in the system of distillation columns.
To reduce the cost of fermentation substrate, one possible alternative as proposed by Zhang et al. Is using renewable lignocellulosic biomass such as corn stover instead of corn kernel. Lignocellulosic is a favorable feedstock since it is the most abundant renewable biomass resource on the planet and it can avoid direct fuel versus food competition. The typical conversion process from lignocellulosic biomass to butanol involves pretreatment, detoxification, and fermentation. However, there's a trade-off for low input costs as during the pretreatment process, a number of fermentation inhibitors compounds are produced due to extreme degradation of lignocellulosic, which may negatively affect fermentation yield.
Another possible alternative is by adoption of biofilm reactor and resin absorption packed bed in the downstream process to increase butanol recovery. Liu et al. Used KAI cross-linked polystyrene framework resin to recover biobutanol from fermentation broth. Compared to the conventional process, the alternative dramatically improved productivity and reduced the energy consumption, as well as water usage in biobutanol production. The reactor has longer service life and are economical to operate with an additional of effluent centrifugation.
The two proposed alternatives are compared based on two criteria: source of substrate and implementation to the current design. Based on source of substrate, Alternative 1 is more ideal as it avoids direct competition between fuel and food source. Based on implementation of the current design, Alternative 2 is more ideal for its simpler and straightforward addition to the downstream recovery process. Alternative 1 is chosen as we feel that avoiding food and fuel competition is more important than the complexity of the alternative process implementation. An input-output diagram is presented. The input materials are maize kernel and water, and the output materials are acetone, butanol, and ethanol. Based on input-output level analysis, the net profit of the proposed design is $15.6 million, and the break-even TCI is $156 million, assuming a minimum of 10% ROI. Market of biobutanol includes fuels, solvent, surface coating, and chemical synthesis intermediate. Other revenue-generating streams include byproducts of fermentation, such as carbon dioxide and hydrogen gas and waste mash. Upon separation, the carbon dioxide and hydrogen gas can be compressed and made valuable. The waste mash is rich in proteins, organic acids, and vitamin B2 and B12, as well as saccharides, making it an excellent animal feed. Referring to the cost breakdown diagram, it is observed that the proposed design requires much more input material. However, the output rate of all three products are also significantly higher compared to the conventional method, generating 380% increase in overall annual revenue. This shows that the proposed design has great potential in overall production profitability and efficiency. To assess the viability of the project from an economic standpoint, a rough estimate of the planned TCI is $217 million, yielding an ROI of 7.5%. However, by increasing the biobutanol unit selling price by 4 cents while keeping all else constant, the break-even TCI is now above the estimated TCI, giving a 10.02% ROI. To sum up, from an economic perspective, the project could be viable if the biobutanol price is slightly higher than the current market price. Other options include decreasing production costs, for example, picking cheaper made equipment, to maintain a relatively lower TCI and the desired ROI.
In conclusion, the project is recommended to be considered in more details for several reasons. First, economically, for a minimum ROI of 10%, the proposed design is viable when the biobutanol selling price is at least $0.45 per pound, at the basis of a biobutanol production rate of 177 million pounds per year. If increasing the selling price is not ideal, the proposed design may be improved by adopting Alternative 1 to reduce raw material costs. Second, environmentally using corn-based biobutanol as an alternative to petroleum-based gasoline is extremely beneficial and valuable as it releases fewer greenhouse gases and is renewable. Third, socially, developing and incorporating of biobutanol production process creates substantial job opportunities, particularly in the agriculture sector. Going on from here, possible next steps include genetically engineering a more tolerating strain and technologies to increase biobutanol recovery and yield.